In this video, we're going to look at logarithms, and it's going to be more of an introductory to logarithms and kind of working our way to being able to determine the value of a logarithm when applied to a number, so that way we can build into analyzing and sketching these functions. Now, logarithms basically, they tell you the exponent that has to be applied to a base in order to produce a desired output. For instance, if I have the function y equals b to the x power, I could rearrange those variables and write it in terms of a log, because what logs equal is they equal the exponent that has to be applied to the base. So that means the log is going to equal x, the exponent, and the base of the log is going to be the same thing. So the base of the log is going to be the same thing that had the exponent. So b being the base of the x is going to be the base of my log. And the desired output is what log is going to be applied to. So y equals b to the x can be rewritten as b log base b of y is equal to x power. So I can rearrange that. And so we're going to evaluate the following logarithms. And so we have log of 1. Now, if you don't see a base of a log, it is an implied 10. That's a common log. So we really have log base 10 of 1. And we want to know, what does that equal? Well, until you get better at working with logs, it's often helpful to rewrite this as an exponential function. So I could rewrite this as 10 to the what power is equal to 1, which gives me 0. So log of 1 is 0. Now let's look at log base 2 of 2. So this one has a base. I want to know, what does this equal here? And so let's say, all right, what does it equal? Question mark. So take the base of the log, raise it to that power. So 2 to the what power equals the inside? Well, that's going to be 1. So log base 2 of 2 is equal to 1. Now log base 5 of 125. Well, let's rewrite this as an exponential form to see what how we would apply this exponent. So 5 to the what power is equal to the inside. So 5 to the what power is 125. That would be 5 to the third power. So log base 5 of 125 is equal to 3. Now we're looking here. Log base 6 of negative 216. We want to know what that equals. So if I rewrite this, 6 to the what power is equal to negative 216. Well, we have a problem here, because I have a positive base 6, and I want it to equal a negative 216 just by changing its exponent. You cannot do that. I can't make a positive base become negative or even. In fact, I can't even make it 0 by changing its exponent. So this is undefined. Now log base 5 of 1/5. Okay, well, we can do this. Let's rewrite this. So 25 to the what power makes 1 over 5. Well, I could use properties of exponents and rearrange this. Let's make that an x. And so 25 to the x power is equal to 1 over 5. I write those as base 5. So that's 5 to the 2x is equal to 5 to the negative 1. And then we see that x would have to be equal to negative 1/2 to make that work. So log base 25 of 1/5 is equal to negative 1/2. And last one here, log base 3 of 1 over 243. What does that equal? So 3 to the what power makes 1 over 243. Well, 243 is going to be 3 to the 1 over 243 is 3 to the negative, what is that, 5 power. So that is going to equal negative 5. Okay, and so we're going to take kind of the same approach. Let's complete the table here. And this is, we would do this if we were trying to make a sketch of what it was we were looking at when we're trying to graph a logarithm to an extent. And so we want to work our way and fill in the table for log base 1/4 of x. So put in 1/4, log base 1/4 of 1/4. That is equal to 1. Log base 1/4 of 1/2. So 1/4 to the what power makes 1/2 is what you're asking yourself. And that would be, if I took the square root of 1/4, so that means the exponent of 1/2. All right, then we go to the next one. Log base 1/4 of 1. 1/4 to the what power makes 1? That would be 0. And we work on our way to put in 2. 1/4 to the what power makes 2? Well, that would be, take the square root of it and flip it. So that would be to the negative 1/2. And log base 1/4 of 4. 1/4 to the negative 1 power is will make 4. Now let's do the same thing, but now we're actually looking at it a little differently. So I want to find the x values with the corresponding y values here. So I want to know negative 2 equals log base 3 of x. How would I do that? Well, let's rearrange it as an exponential function. So that'd be 3 to the negative second power is equal to x. So that means x is really 1/9. And then we keep working our way down. So I say negative 1 is equal to log base 3 of x. Rewrite it as an exponential function. 3 to the negative 1 power is equal to x. So x is 1/3. And then let's see, we got 0. So 0 equals log base 3 of x. And so rewrite that as exponential function. 3 to the 0 is equal to x. X is equal to 1. And let's see, we got 1 now. So 1 equals log base 3 of x. 3 to the 1 power is equal to x. So x would have to be 3. And then the last number left is 2. So 2 equals log base 3 of x. So 3 to the second power would be equal to x, which makes 9. Okay, so now we're going to take the next step forward, and we want to start making a graph of the exponential functions. And to do this, we're going to start with the function 2 to the x power, which we've already learned how to graph these earlier in class. But we'll start by making the table of values. So y equals 2 to the x. We'll fill in the table. So 2 to the negative 2 is 1/4. Then I have 1/2. Then I got 1, 2, 4, and 8. And we'll make a sketch of what goes on here. All right, we'll put our dots in here. So start plotting points. And so here we have the graph of y equals 2 to the x. And we've already know how to do that. Now some features to keep in mind that we have here is that we have a horizontal asymptote of y equals 0. And we have all of those points that we plotted that were really coordinates. And so we had all those points. Now, if I want to graph the inverse of y equals 2 to the x, which the inverse of y equals 2 to the x is log base 2 of x, and we'll algebraically rewrite that later, but that's not in this video, is if I wanted to make an inverse table, basically what you would do is you swap your x's and your y's. So all of my y values become x values. So I'm going to copy my y's in the x row. So 1/4, 1/2, 1, 2, 4, and 8. And I'll match the colors. The y values on this inverse graph are the original x's of y equals 2 to the x. So it'd be negative 2, negative 1, 0, 1, 2, and 3, because of the property of, or the relationship between a function and its inverse. So we'll make a graph here of this. Now I don't have any negative x value, so I'll have my y-axis, and then we'll make our x. And so we connect our dots here, and I went ahead and finished the graph. And the question is, how did I know that this graph was going to bend towards the y-axis and not cross it? Well, our original function, y equals 2 to the x, had a horizontal asymptote at y equals 0. When we go through the process algebraically of finding the inverse, and even when we plotted these points, we swapped our x's and our y's. So that horizontal asymptote of y equals 0, if I swap my x's and my y's, It gives me an asymptote of x equals 0 and x equals a number is a vertical asymptote. So this logarithmic graph has a vertical asymptote at what makes the inside equal to 0. And so that's how I knew it bend at the y-axis and showed that unbounded behavior.